to our fifth and final talk in this series on interpreting veterinary literature. Today's topic, logistic regression, sounds intimidating, but I promise it's more approachable than it looks on the page. By the end of this talk, you'll know what an odds ratio is, how to read a multivariable results table, and how to extract the key clinical messages from the most common type of regression analysis you'll encounter in veterinary journals. Let's dive in. Grid map. Logistic regression is used when the outcome is binary, alive or dead, diseased or healthy, responded or didn't respond. It's everywhere in retrospective clinical studies and case control studies. We'll build from the ground up. What's an odds ratio? How do you read it? And what does adjusted for confounders actually mean in practice? Then we'll apply it to a clinical case. Logistic regression is the workhorse of observational veterinary clinical research. Anytime you see a paper asking, what factors are associated with outcome X? There's a good chance they used logistic regression. Unlike an RCT where you control everything, observational studies deal with patients who differ in many ways: age, breed, disease severity, treatment timing. Logistic regression lets you analyze the impact of one factor while mathematically accounting for all the others. The output is a table of odds ratios, one for each variable in the model. Let's make sure we understand what an odds ratio actually means. Ratio trips people up because we're not used to thinking in odds in clinical medicine. We think in probability. Let's make it concrete. If 1 in 4 dogs exposed to parvovirus gets infected, probability equals 25%. Odds are 1 to 3. For every infected dog, there are 3 that didn't get infected. Now the important point. When the disease is rare, less than 10% of the population, odds and probability are approximately the same. And odds ratio approximates risk ratio. When the disease is more common, OR exaggerates the effect compared to the risk ratio. This matters when you're interpreting case control studies where the outcome is common. Always ask, is this outcome common or rare? If common, be cautious about interpreting the odds ratio as if it were a risk ratio. It's the concept that separates a useful regression paper from a misleading one. Imagine a study finds that Great Danes have higher GDV mortality, crude odds ratio of 2.8, but Great Danes are also older on average and more likely to present in shock. If you don't adjust for age and shock status, you don't know whether it's truly the breed driving the mortality or the confounders. Multivariable logistic regression adjusts for all of those factors simultaneously, giving you an adjusted odds ratio that tells you, after accounting for age, shock, and time to surgery, what is the independent effect of breed. Always check. Are the odds ratios in the paper adjusted or unadjusted? Unadjusted odds ratios in an observational study should raise a flag. Look at how to read a regression results table systematically. Go row by row. For each variable, first look at the OR. Is it above or below 1? Above 1 means this factor is associated with increased odds of the outcome. Below 1 means it's associated with decreased odds. Then look at the confidence interval. Does it cross 1? If yes, not statistically significant. If no, it is. For categorical variables like breed, always check the reference category. OR equals 2.45 for Great Danes means 2.45 times the odds compared to the reference breed. The reference group is always 1, even if you don't see it listed. Papers now visualize their regression results as a forest plot, the same format we saw in Talk 2. but now showing adjusted ORs from a regression model rather than pooled RCT results. Note the log scale on the x-axis. This is standard because it makes the plot symmetric. OR equals 0.5 and OR equals 2 are equidistant from the null at OR equals 1. If the scale were linear, protective effects would be squished near 0. Read this exactly as you read a meta-analysis forest plot. Color coding tells you direction and significance. CI width tells you precision. Pre-op shock has the widest confidence interval, still significant because even the lower bound is well above 1, but it reflects fewer events in some strata. Before we get to our case, let me flag the 4 pitfalls most likely to mislead you. First, the rule of 10. You need at least 10 outcome events per predictor in the model. A study with 50 deaths should have at most 5 predictors. Models with too many predictors are overfit and unreliable. Second, ORs without confidence intervals. Some older papers only report p-values. Insist on the CI. It's the only way to assess effect size and precision. Third, unadjusted ORs in a table labeled ambiguously. Read the methods to confirm whether ORs are adjusted. Fourth, don't interpret a non-significant OR as proof that a factor has no effect. A wide CI with OR equals 0.7, CI of 0.3 to 1.5 is not no effect, it's uncertainty. The true effect could be quite large. Let's work through this case question systematically. The outcome is recurrent urethral obstruction. Let's go row by row. Perineal urethrostomy. Adjusted OR equals 0.38. CI is 0.2 to 0.72. Does not cross 1. Significant. PU is associated with 62% lower odds of reobstruction compared to cats managed medically. This is a meaningful protective effect and is statistically robust. Body weight. OR equals 0.88 per kilogram. Each additional kilogram of body weight is associated with 12% lower odds of reobstruction. CI is 0.79 to 0.98, doesn't cross 1, significant, though the effect per kilogram is modest. Azotemia at presentation. OR is 2.9, CI 1.55 to 5.43, highly significant. Cats presenting in renal failure have nearly 3 times the odds of reobstruction. This is your most powerful risk stratifier. Indoor only, OR equals 1.15, CI 0.72 to 1.84, CI crosses 1. Not significant. Indoor lifestyle is not independently associated with reobstruction in this model. How to explain PU to a client. The data show that cats who have the surgical widening procedure have significantly lower odds of blocking again, about 62% lower compared to cats managed with medical treatment alone. It's not a guarantee, but it's the most impactful intervention in this study. Key lesson. Read each OR systematically. Direction, magnitude, CI, significance. Use adjusted ORs. Don't overinterpret non-significant variables. Series on interpreting veterinary literature. Let me do a lightning recap of all 5 talks. Talk 1, p-values tell you about consistency with the null. CIs tell you about effect size and precision. Use both. Talk 2, RCTs reduce bias. Forest plots pull evidence. Check heterogeneity. Talk 3, Kaplan-Meier curve shows survival over time. Read the numbers at risk table. Hazard ratio quantifies the difference. Talk 4, vaccine efficacy is relative. Also calculate the absolute risk reduction and number needed to vaccinate. Context matters. Talk 5, logistic regression gives adjusted ORs. Read direction, magnitude, and CI. Trust adjusted over unadjusted. The overarching lesson: no single statistic tells the whole story. Always read the numbers, the confidence intervals, the methods, and the clinical context together. Thank you for joining me in this series.